Good day to all. I would like to share about the predictive modeling of student academic performance. Our course focus: Advanced Mathematical Methods. I am Hafizah Bahaludin, with Amirah Busul Aklan. We are from IIUM. We use machine learning to forecast academic risk. We address the too late problem. Intervention is often impossible after final grades. We need real-time risk assessment. Traditional grading is reactive, not proactive. Students fail when help could have worked. Our goal is proactive prediction. We built ML models to identify high-risk students early. We use continuous assessment data for forecasting. This allows for timely, effective academic support. We aim to save the semester, not just grade it. We set two main objectives. First, identify the best temporal stages for intervention. We test 3 stages: early, mid-semester, and full. Second, we must identify the strongest predictive components. Which assessments matter most? Our third objective is model comparison. We compare regression, predict score, versus classification, predict risk category. Our final goal is to develop intervention recommendations. These must be practical and data-driven for our institution. Our study focuses on advanced mathematical methods. This is a mandatory, cumulative undergraduate course. Failure rates can be high. Our dataset spans 4 semesters of student assessment marks. The data is anonymized for privacy. The Continuous Assessment Mark, CAM, is our target. CAM totals 60 marks. Components include quizzes, assignments, a major midterm exam, and a practical project. Each component assesses different skill sets. For classification, we defined 4 performance categories. These are based on the 60-mark scale. The most critical is at risk, scoring below 41 marks. Our models must accurately flag this group. Our methodology simulates the academic timeline. We first conduct feature selection. Then, we apply ML algorithms across 3 scenarios. We test both regression and classification techniques at each stage. This is the first checkpoint. We only use Quiz 1 and Assignment 1. This is just 16.7% of the total marks. Can we predict failure this early? This is the earliest point for a low-cost intervention. This is the critical scenario. We add the results from the comprehensive midterm exam. We now have 83.3% of the assessment data. We hypothesize this is the optimal intervention window. The midterm should be the inflection point. For exact score prediction, we used 5 regression models. These include linear and ridge regression. We also used tree-based models, decision tree, random forest, and gradient boosting. They test linearity versus non-linearity. For risk categorization, we used 5 classification models. This includes logistic regression. We also used decision tree, random forest, and gradient boosting classifiers. Classification output is more actionable for tutors. We used strict evaluation criteria. For regression, we use RMSE to measure error magnitude. For classification, we focused on accuracy and the F1 score. F1 score handles the at-risk class imbalance well. Now, we move to results and discussion of the project. First, we analyzed Pearson correlation. This shows the linear relationship between components and the final score. The goal was to identify the most predictive feature early on. The visual result is striking. The midterm exam has an extremely high correlation, 0.930. Assignment 2 is negligible, only 0.156. Comprehensive exams predict success, minor assignments do not. Early prediction, scenario 1, was poor. R-squared values were close to 0 or negative. The RMSE was high, over 5 marks. We cannot trust early, minimal data for precise score prediction. Look at the mid-semester results. Performance improved drastically. Linear and ridge regression achieved R-squared values over 0.95. The RMSE dropped to about 1.4 marks. Midterm data provides near-perfect predictive accuracy. When all assessment components were available, linear regression achieved near-perfect prediction, confirming that CAM is mechanically the sum of its components. Classification of students into performance categories proved challenging with limited early data. Logistic regression achieved the highest accuracy of 57.1%, only marginally better than random chance for 4 classes. Performance greatly improved post-midterm. The decision tree classifier performed best. Accuracy reached almost 79%. Gradient boosting was close. This accuracy level is viable for real-world academic decisions. The decision tree classifier achieved high metrics. Precision was 0.857. High precision is crucial for intervention. It minimizes false alarms, saving valuable resources. The model reliably identifies those who truly need help. We used random forest to find feature weight. The midterm exam accounted for approximately 90% of the predictive power. Small, low-stakes components are largely noise. The midterm is the dominant signal. Then, moving forward for the discussions, we identified the midterm inflection point at week 9. Prediction accuracy increases by over 200% at this stage. This is the optimal window. Intervention is high confidence and timely. Focus resources here, not earlier. We used random forest to find feature weight. The midterm exam accounted for approximately 90% of the predictive power. Small, low-stakes components are largely noise. The midterm is the dominant signal. Finally, we have to conclusion for all the results obtained. Early prediction is inaccurate. Post-midterm prediction is highly accurate. The midterm is the single most critical signal. Recommendation: adopt a mid-semester checkpoint strategy. Implement a decision tree model after the midterm results. Use this tool for targeted, timely, and high-confidence student support. Thank you for your time.